Hello everyone, Teacher Samuel here. I want to welcome you to our today's session, and today I want to take you through a concept in electrochemistry under what we call the standard reduction potentials. When we talk about the standard reduction potentials, our focus is on redox reactions. And as a student, the question is, have you heard of redox reaction or that term, redox itself? So redox, it is more of an acronym which represents two things. On one end, we have what we call reduction, and we have ox to represent oxidation. So we can define these two terms in terms of transfer of electrons. Define reduction as the gain of an electron. So any substance that is going to gain an electron, then we are going to conclude that substance have undergone reduction. On the other hand, we shall define oxidation as the loss of an electron. So in chemistry, if a substance loses an electron, then we say it has undergone oxidation. So now with those two terms in mind, let us focus on the table. We can be able to see that on this table, we have some positive values and some negative values. But there's something I want us to focus on. We have hydrogen. And if you are keen, I want to highlight it. So hydrogen, there it is. So it has been assigned as 0.00 volts because these reduction potentials, they represent the concentration of an electron within an electrode. So we shall compare the ability of an element either to gain an electron or lose an electron with reference to the hydrogen half cell. I've introduced another term, a half cell. So I'm going to explain that later. So if you have an element that has high ability to gain an electron more than hydrogen, then we say it undergoes reduction. And because of that, it is assigned a positive standard reduction potential. On the other hand, if an element has a greater ability to lose an electron more than the hydrogen, then it is going to be assigned what we shall have as a negative standard reduction potential. So with that in mind, it means we can subdivide our the standard reduction potentials into two parts. So there are those that are below hydrogen and those that are above. So all those that have positive values, then we are saying they have the highest ability to undergo reduction. And those that are below hydrogen, or rather those that are negatively charged, they have the greatest tendency to undergo oxidation. So as a student, once you are able to understand, to interpret these values, then it becomes very easy for you to solve any given question under this concept. Similarly, at my far end, there are some terms which have been written as being the strongest oxidizing agent as well as being the strongest reducing agent. So we have two terms, that is reducing agent and what you call oxidizing agent. So when we talk about a reducing agent, a reducing agent is simply the substance that undergoes oxidation. So we are simply saying if a substance can easily undergo oxidation, then we say it is a strong reducing agent. On the other hand, we have oxidizing agent. Oxidizing agents, these are substances that can easily undergo reduction. In other words, they easily gain electrons. So it's like we are going to interchange these two terms. On the other hand, on one hand, we have reduction and oxidation, which we have defined. Now we have introduced reducing agents and oxidizing agents. So we are going in a simple way to say reduction goes with oxidizing agents. Then oxidation goes with reducing agent. Because oxidizing agent easily undergoes reduction. On the other hand, reducing agent easily undergoes oxidation. So as a student, this is the simplest way in which you can be able to know what is a reducing agent and what is an oxidizing agent. So you just need to understand reduction goes with oxidizing agents. Oxidation goes with reducing agents. So we go back to our table. We can therefore say, if you look at fluorine, we can be able to see that fluorine has positive, there it is, with positive 2.87 volts. So we can therefore say it is the most positive. So by being the most positive, therefore means it can even undergo reduction. Therefore, this makes our fluorine to be the strongest oxidizing agent. So we are going to have this one as being our strongest oxidizing agent. So we are saying the more positive the standard electrode potential is. Then you also have lithium. So lithium on our case, it is negative 3.04 volts. So we can therefore say it is the most negative. So what do you mean by that? By being the most negative, it means it is the one that can easily undergo oxidation. So by being the most negative, therefore means it is the strongest reducing agent. So as you move down, the more negative the standard reduction potential of an element is, then we conclude it is the strongest reducing agent. Then the more positive the standard reduction potential value is, then the strongest oxidizing agent. So we come back to where we have our hydrogen. So you can see we are referring everything we have to hydrogen. So because of that, we shall use our hydrogen as our reference electrode. And that is why our hydrogen has been assigned uh, a standard electrode potential of 0.00 volts. So we shall compare everything from hydrogen. And that is how we can be able to interpret the standard reduction potentials. We've been able to see how we can be able to interpret the values based on redox reactions. I would like us to have an example to see how we can apply this knowledge of getting to know what undergoes reduction, what undergoes oxidation, as well as in terms of reducing agents and oxidizing agents. Look at this question together, see how we can be able to apply the knowledge you have acquired to solve an examination scenario. So we have been given a question here. We have given some half reactions, and also we have some electrode potentials. So as you can see, these half reactions are what we call reduction. So we call them the reduction half reactions because they represent reactions in which elements are gaining electrons. And of course, we have our hydrogen. Let me just circle it for clarity. So there we have our hydrogen. As you can see, it has been assigned. So this is going to be our reference. So the mistake that students make is to rush into the questions given. The first thing you're supposed to do, you have been told, study the information. So we need to interpret the information even before we go to the questions. From what I can see, we have some positive values and also some negative values. So the question is, those that are positive, what did we conclude? So remember what we said, if they are positive electrode potentials, it means these electrodes have the greatest ability to gain an electron more than hydrogen. So therefore, easily undergoes reduction. Then those that are negative, it means with reference to hydrogen, they have the greatest ability to lose an electron. Therefore, they undergo oxidation. And this is the first point where a student should start from, by first of all interpreting what these values mean. So that now we know, like in our case, E is the most negative. Then we have our, let's use a different ink. We have our E with plus. So it is the most positive. So that with that information, now we are able to answer our question. Let's go to our first question. It is asking, state the standard conditions of an electrochemical cell. Now, there's something we call an electrochemical cell, and an electrochemical cell is majorly formed when we have two half cells that have been joined together by use of a salt bridge. When the two are connected, and of course we have a voltammeter, then they make what we call an electrochemical cell, which I want us to look at together. And on this diagram, we can be able to see that on my left hand side, I have what we call a magnesium electrode. This magnesium electrode is going to be dipped inside a solution containing 1 molar magnesium nitrate. So together, this is what makes our magnesium half cell. So we can call this, the whole of this, a magnesium half cell. On my right, I have what we call an electrode that is lead. It has been dipped inside a solution containing 1 molar lead 2 nitrate. Again, this becomes what we shall call the lead half cell. So here we have two half cells. We have the magnesium half cell, then we have the lead half cell. Now, to connect them together, there's something we call a salt bridge. And a salt bridge is made up of a piece of filter paper that is going to be dipped in a saturated solution of potassium nitrate. And it has its role, as you can see, it is to maintain electrical neutrality by allowing ions to flow. In other words, it ensures there's a balance of charge. So as the positive and the negative are flowing, then it maintains that balance. Then we have a voltammeter. So the work of the voltammeter, it is the one that measures the potential difference. So the potential difference, in our case, we shall later call it the EMF, what we call the electromotive force. So it is measured by a voltammeter. So of course we have the flow of electrons, as you can see. Now we have the electrodes on my left hand side, and then we have the electrodes on my right hand side. So one of them represents the anode, and the other one represents the cathode. So in this case, maybe the question will be, both of these are metals. And now the question is, between magnesium and lead, which one is the most reactive? So definitely we have the reactivity series. So we have magnesium being more reactive than lead. So we all know metals form ions. So we know that metals are going to form ions by doing what? By losing an electron or electrons. So what do we call loss of an electron? Good. Oxidation. So we shall ask ourselves, between lead and magnesium, which one can easily undergo oxidation? So it's magnesium, because magnesium is more reactive than lead. So in this case, because magnesium is more reactive, then it represents our anode, then our lead represents the cathode. And we are going to see that at the anode, that is where we shall have oxidation taking place. And at the cathode, that is where we are going to see reduction taking place. So in this case, without referring to the standard reduction potentials, I can assign the anode and the cathode by looking at the reactivity, or in terms of which one can easily lose an electron more readily than the other. That's why you can see now it has been indicated that our anode, that is where we have oxidation taking place. As we have concluded, magnesium becomes the anode, oxidation takes place. On the other hand, we have our cathode, where we have reduction taking place again. So here there are two terms, oxidation again and reduction, which I want us to represent in terms of transfer of electrons and oxidation being loss. So we are saying magnesium, which is now in solid state, it is going to dissolve. And by dissolving, it means it loses electrons, and electrons are going to enter into the solution. So this is what we call an oxidation half equation or reaction. So our magnesium, see the magnesium, as you can see, so the magnesium, we are being told it goes into the solution. And by doing that, so we have now the magnesium ions. So that reaction is what we are calling oxidation. On the other hand, we can also have what we call the reduction half equation. So we shall start with lead ions. So as you can see, the lead ions are in the solution. So they are going to be attached on our electrodes. So by doing that, we are going to have some deposition. In other words, the mass of our cathode is supposed to increase, whereas the mass of anode is supposed to decrease because more magnesium is being, or rather goes into the solution, while the lead is being deposited at the cathode. So we can also represent, because reduction is the gaining, so it's going to gain 2 electrons to become Pb. So, and that explains why the mass of our anode decreases while the mass of our cathode is going to increase. So again, we are going to have the reduction half equation. So this is what we call an electrochemical cell, which is made by combining the two half cells. So we have the magnesium half cell, we have the lead half cell, are joined together, or rather they are connected by use of a salt bridge. And of course, we have the voltmeter that is going to measure our EMF. We also have the flow of electrons, as you can see, that electrons are going to flow from the anode, moving all the way to the cathode, as they are being shown. So that is what we call an electrochemical So we are being asked, state the standard conditions of an electrochemical cell. If you are keen, there are two conditions. Number one, we had the electrolytes. Both of the electrolytes, their concentration was 1 molar. So one of the conditions that you are going to see is that we shall have 1 molar, 1 molar, uh, 1 molar of electrolyte. So whatever is going to be used, it must be 1 molar. The other standard condition that we must be able to measure the reduction potentials under is temperature. And in this case, temperature, we use the room temperature, which is 25 degrees Celsius, which we can convert to be 298 Kelvin. We always have another condition, that is pressure of at least 1 atmosphere. And those are the three conditions that must be maintained whenever we want to measure the electrode potentials. Let's move to the second question. Identify the electrode that is the strongest reducing agent. So the keyword is reducing and of course strongest. So we ask ourselves, reducing agent goes with which term? Reducing goes with oxidation. Very nice. Now, with oxidation, we need to revisit what we had covered earlier. That for oxidation, we are going to assign positive, or rather, sorry, we are going to assign negative values. So we need to ask ourselves, where we have the standard electrode potentials. So our focus here is going to be on the negative values. So we ask ourselves, because the word is the strongest, so which one is the most negative? So if you look, how many values are negative? There are three: negative 0.13, negative 2.87, and negative 2.71. So which is the most negative? Then from the look of things, that makes G. So we can now conclude G with negative 2.87 volts. It is the strongest reducing agent, and that becomes our answer. Then we have the second part that is asking us, again, the strongest oxidizing agent. When it comes to oxidizing agents, our focus, remember the terms are opposite of each other. Oxidizing goes with reduction. From what we covered, reduction, our focus is on the positive values. So we go to a table. There are three actually, values that are positive, plus 0.80, plus 0.68, and plus 0.34. So we need to ask ourselves, because the word is the strongest, which one is the most positive? So and in our case, we have plus 0.80, that makes E, which is plus 0.80 volts as our strongest reducing, or sorry, oxidizing agent. So you see, the moment you are able to interpret the positive and the negative values, then answering the questions becomes very easy. Next question, you are being asked, you're supposed to state two half-cells when combined will produce the largest EMF. So here there are two terms. So we can have largest EMF. So when you want to get the largest EMF, our focus is on two things. Which one is the most positive and which one is the most negative. In our case, I think you've been able to know that is G and E, G and E. So this question can also be asked in terms of the least EMF. So just like we had the most positive, so here you're going to focus on the least positive and the least negative, because this is a possible scenario where you can be asked which one has the least EMF. And going by that, you can look at the least negative. The least negative is negative 0.13, and the least positive is plus 0.34. So that makes us D and H. So we have D and H in no given order. So that is how we can be able to determine which one will give us the largest and which one will give us the least EMF. Move on to the next question. The question is asking, calculate the EMF. So calculate the EMF of the cell identified. So we're able to see that we had G and E. So now the question is, how do we calculate the EMF? So the EMF, which you are going to see in most cases abbreviated like that, the E naught of the cell. So we have a formula that we use whereby we say the EMF is given by the electrode potential for reduction to subtract the electrode potential for oxidation. So if you go back to what we had covered, we saw in our case which one undergoes reduction, which one undergoes oxidation. So we saw that G undergoes oxidation. Then our E undergoes reduction. We're going to work it out. So reduction, we shall have plus 0.80 minus 287. So when you work it out, it's plus 0.80 plus 2.87. And in our case, if you have a calculator, you can be able to work it out plus 3.67 volts. So it means our EMF for the E naught of our cell will be equal to plus 3.67 volts. Now, what is the mistake that most students make? Students, most of the time, they tend to omit this positive sign. And remember, if you omit that, then you lose half a mark. In other words, you will not get any mark on the answer. Meaning, even if all the other working was correct, the maximum you can score will just be a half mark. So always remember the EMF must have a sign. So always assign that sign. And in most cases, the EMF is always a positive value. So rarely do you work it out and you get a negative sign. So if you're going to work it out and you find it's negative, that should tell you you need to go back and relook at your working, because that means something could be wrong somewhere. So that's how we calculate the EMF. And again, this formula, remember, the formula in this case has no marks. However, in an exam scenario, if you write the wrong formula, then you are penalized half a mark. So always ensure if you must write the formula, then it must be correct to avoid any penalties or other attracting any penalties. Good. From 1-5, you asked write the equation for the reaction. So here we have two cells. So we have G and E, and you also have one undergoes oxidation, the other undergoes reduction. In other words, you are being asked to write the half equations. I want to encourage students to always start with oxidation half equation, because with oxidation, you're able to know how many electrons were lost. Always try and start with oxidation half equation. So the oxidation was taking place in G. So let us go back and see. So G has an oxidation state of +2, or the charge is 2. And E, remember, has an oxidation state of +1. That's very important. So we are saying G undergoes oxidation. So G goes into the solution. Start with a solid. It must lose to become G plus. So it loses 2 electrons. And that is the equation for oxidation. Remember the physical states. Always try, if you are going to attach them, make sure again they are correct. Then we shall have the reduction half equation. In our case, E undergoes reduction. And there's something that we must note about E. What is the charge on E? +1. So meaning E was able to gain 1 electron so that it can be able to form our E. So now the question is, how many electrons were lost at the anode, and how many electrons were gained at the cathode? We can see 2 electrons were lost. So here we have 2 electrons lost, but only 1 was gained. So we must balance number of electrons. The number of electrons lost must always be equal to the number of electrons gained. So what do we do to balance the equation? So what we do, we take a whole number, or we can call a coefficient, to multiply both the equation so that we can balance the number of of electrons. Allow me to extend this space. So we start with G for oxidation. We had G solid to give us G2 plus aqueous plus 2 electrons. Then we had E plus gaining a single electron to give us the E solid. So we can see the number of electrons are not balanced. So what do? We take the whole of this oxidation reaction, we multiply by 1, and we take the whole of this reduction half equation, we multiply by 2. So with that, what becomes of our equation? So G remains the way it is. It is G solid becomes G2 plus aqueous plus 2 electrons. Then we shall have E, we shall have 2 electrons in aqueous plus 2 electrons, sorry, to give us 2E in solid state. So after that, we need to combine these two equations. So how do we combine the two equations? So we remove what is common. So in our case, we cancel out the number of electrons because they are now balanced. So they have no use to us now. So you cancel this, so they cancel each other. Then we now combine the remaining equation. It is G in solid state plus 2 electrons in aqueous state to give us our G2 plus aqueous plus our 2E in solid state. But now there's something we must attach because you have been asked to write the equation for the cell reaction. So we must attach the EMF, which we found to be plus 3.67. So at the end, we are going to attach our E naught of the cell, which is the EMF, plus 3.67 volts. And that becomes our cell reaction. So that becomes our cell reaction. So the most important bit is to always ensure whenever you are writing the half equations, the number of electrons must always balance. So here, we must always balance the number of electrons. So this question can also be asked in another way, whereby you may be told you write what we call the cell notation, or what we call a cell diagram. So instead of drawing, you can represent. So this is simply, it is just a representation of an electrochemical cell, of an electrochemical. Instead of drawing it, how would it appear if you are to just represent? So there's a conventional way of writing it, whereby the half cell, where oxidation takes place, which is the anode, must always be on the left hand side. And in this case, G undergoes oxidation. This is how we are going to write it. So we start with G, so a solid. In a half cell, we must separate the opposite charges. So G gets to G plus, G2 plus aqueous. That is our half cell. Then the two half cells are joined together by what we are calling a sword bridge. Then we have our two E electrons in aqueous state, which are separated from the two E in solid state. So this single line, we call it a phase boundary. It separates the positive and the negatives. Then we are going to attach our EMF, which is going to be plus 3.67 volts. Again, this becomes our cell notation, or what we can call our cell diagram. So that's a possible question that students can be asked. So it is good that as a student, you're able to understand that on this other end, so we have our anode on the left hand side where we have oxidation take place. Then on this end, we are going to have our cathode where we have our reduction take place. Then not forgetting now, we have these two vertical lines which represent our solid bridge. So it is simply a representation of what would appear if we were to draw. But again, as a student, it's also important what if you are asked to draw, because it's also a possibility to draw the electrochemical cell. How do we go about it? So you must remember that an electrochemical cell must have two half cells. So in other words, we must have the G half cell being joined to the E half cell, or rather being connected to the E half cell by use of a salt bridge. So to start off, I'll just draw um, my G electrode. I have it here. Don't worry about the shape. Mm. Then of course I'm going to bring in the issue of a salt bridge. Before I bring the salt bridge, let me draw the other half cell. So I'm trying to bring in my salt bridge. I should have used some different ink so that you're able to see and follow what is happening. So we are going to connect these two. There we have our voltmeter. So we can label it. So this is our electrolyte. And remember, the first question was asking which are the standard conditions. So it means if we are going to have this as our G electrode, our G must be dipped in 1 molar solution containing G ions. Same case, if we are going to have our E, this is our E electrode, it must also be dipped inside a solution of 1 molar containing E in aqueous state. Then of course we shall have our salt bridge. We have a voltmeter to measure the EMF. We have the connecting wires. And don't forget, you can be able to show how electrons are flowing because this becomes our anode, this becomes our cathode. So whatever I have there is what we call now an electrochemical cell, whereby we have on the left hand side, we have our anode where oxidation takes place. Then on the right hand side, I have my cathode where reduction takes place. And the two half cells are connected using a solid bridge. And don't forget, the standard condition must be our electrolyte must be 1 molar. So we are saying this one, you must remember it must be 1 molar solution. So I believe I've been able to take you through the concepts of the electrochemistry, sorry, and the focus was on the standard reduction potentials. I hope you find this lesson uh, and hopefully you're going to find this lesson of importance to your revision and keep following for more. See you in our next session. Thank you so much.